So OR2K, basically we need to do something about code density, and we can't really do it with OR1K. And it'd be nice if we could just start again. I think that there's no reason to really rush into this because we're still getting a lot of stuff done on OR1K.
Yeah.
But I think it's a good learning experience for everyone who's involved in the development of that stuff, because we're going to probably do it all again, for OR2K, or we're going to be able to use a lot of the work that we put in now and expertise and stuff.
But basically these two camps, those who want to do something based on the current architecture, those who want to do something completely new and radical.
Maybe.
Well, we had that debate about a year ago, and we agreed that it wasn't going to be backwards or forwards compatible, but it would be inspired by, I think it was the description. So it's not a radical architecture, but neither is it a compatible.
It's improvements that you can't do.
Yeah. We're allowed to break what we have already.
Yeah. No backward compatibility. We can live without that. Yeah, there's a link on the OR2K page. So that's the goal of an instruction set. What I've got there is a set of instructions that I think we're going to have. I can talk through the branch condition stuff that I've put together.
You've effectively defined it to be 32-bit.
Which, so the stuff in light blue is 16-bit instructions. The stuff in...
No, what about 64?
64. Oh, sorry, yeah. That's right. In my post to the mailing list, I said mixed 16-32 instructions, 16 GPRs.
I'm not talking, not.
Maximum data width of 32 bits.
Right.
So, where are we? This is a mailing list post.
When was it sent?
August 7.
You need to reply.
Oh yeah, okay, got it. I didn't reply. I think the maximum data width of 32 bits is a shame. And there's a retrograde step. Because OpenRISC 1000 allows 64 bits, and every man and his dog seems to be bringing out 64 bits.
I'll tell you what I'm really targeting this at, though, is embedded processor use.
Well, so's ARM.
I disagree. ARM have just brought out a new 64-bit ISA, which is targeted at services, right?
Well...
If you want some 64-bit ISA, I reckon you're going...
That's what I'm looking for.
It'll end up in phones in a year or two. It'll be in phones.
But,
as application processors, yes. But I'm not talking about this stuff as application processor core thing. I'm talking about this as an embedded processor that gets used in ASICs and FPGA.
is there a case for 8 instructions?
Sorry?
Is there a case for 8 instructions?
I thought about that. I don't think there is.
No, not the intelligence.
But that's my use case, right? Like, I want to be able to, at work, go and see these boys pick up OpenRISC or other ASIC companies or other small, people using embedded.
And your purposes for doing 16-bit is to get code density.
But I honestly think that there's a big use case for these processors. And for a group as big as we are, we can't take on something the size of OpenRISC 1000. Like in terms of what they're trying to be. Floating point, vector units, 64-bit, there's just too much stuff there to develop hardware and software for and test it. I think what this group is probably quite good at doing is, getting together and doing a nice embedded microprocessor that is applicable, that can be used in embedded situations, right? That's what I really think we'd be very good at doing. And so we should... See you, Frank.
Okay.
Thanks for coming, mate. Really nice to meet you.
Yeah.
Hope we can do it again.
Yeah,
Nice to meet you, Frank.
Bye. Nice to meet you. Bye, guys.
Yeah, that's my thinking, is that we, that's what we're capable of. I don't think we should be going and, talking about 64-bit wide.
Yeah, but I mean, but what my thinking was not say we must do a 64-bit one, but OpenRISC 1000 is conceived as an architectural framework that allows you to do 32 or 64-bit implementations. And I'm not saying it's the wrong answer. I think it's just saying, you may choose to do an implementation that's one particular size, but should you constrain yourself, though, so that 5 years down the line, we say, what a shame we didn't allow OpenRISC 2000 to be extensible to a 64-bit world.
Or should that be OpenRISC 3000?
Well, maybe it should be. I mean, maybe we're saying OpenRISC, something that OpenRISC 1000 didn't actually officially specify, but there's a lot of history showing people tried to do, was to do a 16-bit processor. I mean, should there be something here saying about actually allowing us to do 16-bit
data
implementations? Yeah.
Yeah, in OR2K.
Yeah. I mean, actually going down into some of the AVR space.
Or MSP.
Someone's calling. Is that Ben? I think you're calling us.
Okay, call the Roman. Okay, I got both numbers.
Okay, cool.
So this is Michael. Okay.
All right. All right. Jeremy, the fact of the matter is, though, that for 13 years, OR1K has sat there specifying 64-bit stuff, and not a single implementation or bit of software has been written that uses it.
Yeah. Yeah, I'm not saying it's wrong. I'm just asking the question.
Yeah, I know. I'm discussing it. I do think it's a big call to say that we're pretty much going to limit ourselves to 32-bit data.
I mean, I'd quite like to say if we're going that way, we ought to also explicitly say, and this time we'll consider allowing us to do 16-bit as well. So, if you're saying this is actually aiming at more detail embedded, which is the bit that interests me. Anyway.
This ties in a bit to my thoughts on the processor architecture optimized for FPGAs, which I haven't really presented anywhere, but currently I have a bit of planning and basically no documentation or code, but it would be interesting if an instruction set could be found that is suitable for the architecture. In essence, it would take a CISC-like loop extension, but with RISC-like operations, so that it would do serially operations of an arbitrary width.
Oh yeah.
Since using one block RAM, you can generally right now, if you implement a CPU with block RAMs for the register file, a lot of that block RAM gets wasted because it's a lot deeper than it's wide. Yeah. One way to avoid that is with the fast context stuff. So I was thinking a processor that could well compute with 32-bit or 64-bit data, but only use an 8-bit wide register file and use a higher clock instead, so automatically carry up the carry chains.
I don't think that would be something that you'd need to specify an architecture spec, though. That would be an implementation trick.
It absolutely could be, but that architecture would easily lend itself to an architecture which could adapt from 8 to, say, 128-bit operation.
Are you talking about data or instruction words here?
Data.
Yeah. Fine. I mean, you could fundamentally change the immediate width of this ISA, which is sort of what happens in OR1K, I think, when you got 64-bit. It's just the data width changes, and I don't know, your extension 0 and sign extensions all matter. So 32-bit data.
Yeah, that's usually what you do there.
So, sure. But then again, I mean, that wouldn't be a mainstream sort of processor that a lot of people would look to use, I would think, if you had sort of arbitrary width data processing.
I don't think that feature is that attractive for mainstream use, but the architecture itself lends itself to, in current FPGAs, a very compact implementation, one which trades clock cycles for compactness of logic.
And that's what the 7 points.
Yes, it is asked for.
What's asked for?
A compact processor that can execute general purpose code, including larger memory spaces.
Yeah, I mean, what's the smallest FPGA that you would put in these days? I mean,
Igloo Nano.
sorry?
Igloo Nano.
Okay, I mean, how big is that? What sort of processor did you put on there?
I'm not sure.
The one is at 200.
Yeah, 250,000
Okay.
logic elements, whatever that is. Yeah.
But you could easily fit an OpenRISC in that.
No.
I don't know.
You could fit a Micro 8 easily, probably, but
Not a risk.
too big.
Like the LH9 microboard, but you have one, right? I couldn't see the OpenRISC and the Ethernet Mac on it. Basically, OpenRISC took about almost all of the resources.
The Ethernet Mac happens to be a hog as well, but
Yeah, but
So, I mean,
But I mean, I guess you're talking about the instruction set architecture. I'm sort of saying it probably needs at the beginning. We've got some broad words on that thing that says it's not backwards or forwards compatible, but it's philosophically the same. I think possibly before you get down into what the ISA is, it's worth actually saying, and this is, you know, intended to be operating in the 16/32-bit data space. Explicitly, it's not a 64-bit. That's a separate project, you know.
I guess so. But there's nothing to say that you can't extend this ISA to add whatever support you need to have 64 bits.
Well, unless you structured it such that, when I want to put the next instruction in, the decoding turns into a nightmare.
like the x86.
Yeah.
One of the first extensions they added was redefining the POP-CS instruction, which loads the upper bits of your program counter, which is a rather weird operation.
Yep.
Well, I mean, yeah, but I mean, that's the proof that, you know, if you're a big enough company, you can have a completely rubbish architecture and still sell it millions.
Yeah.
So I'm, basically outlining. I understand that before you go on and talk about instruction encoding, you need to, you know, frame your proposal with what
we've
you
got an
actually
overview
intended to do with this thing and what, you know.
Shall I put it in there? I could edit it straight away.
But I mean, I'm just saying, this is what I'm going to discuss and propose, because I have sat down and had a bit to think about this. I have worked in an ASIC company for the last year and seen them, you know, seeing what processes they use and the reasons why. And I just want to get to a stage where we can, all the criticisms that they have of, say, you know, the current flock of open source processes, get to a point where that doesn't apply.
Yeah. Well, it's a reason.
Is a big one. And these guys aren't sitting around doing,
let's put some notes in there.
Computations internally. They're doing a lot of, you know, M0s, stuff like that. Data shuffling. There's even an argument for, so there's guys at the moment who are sitting next to me who are using 8051 to do a lot of their stuff. And they are even saying, we want something even smaller than an 8051 to do what we need. So, I mean, you can't please everyone, but I do think if you had a reasonable processor that ran, you know, some efficient, code-dense control software that had, you know, good sleep modes and interrupt control and stuff like that, then you would get a lot of people using it.
Yeah.
So the implementation area is one thing. That's why I've chosen 16 GPRs. I mean, but that's something we can experiment with, right? So that's something where you go and look at whether your code gets bigger or smaller with 16 or 30.
Yeah, I mean, I just think that the constant refrain I get from Jörn is that the architectures like ARM and ARC are register starved when it comes to GCC.
So Jörn's not sitting around spending money on silicon, is he?
Optimizing compilers. On the contrary, ARM he's working for people like ARC who care passionately about this and have split 32 16-bit instructions unaligned. So
he's not designing ASICs with register files that are twice, you know.
He's doing exactly what you're trying to do. He's working for people whose passionate concern is, how do I make this smaller? Okay, and he comes back to them and says, yes, but this is a false economy, because yes, you've made it smaller, but you've completely screwed your performance because you haven't got enough registers for a modern compiler.
All right, I may stand corrected, but It doesn't seem. Yeah, maybe it's false economy, right?
Yeah.
It doesn't seem that way, but maybe.
Sorry?
Yeah.
I'm suggesting that even if you want small programs, if you want to be compiled, 16 registers is too few.
Yeah, I say 32.
Yeah. There we are. See, another compiler writer agrees.
That's for working on LLVM.
That was good. That was the right answer, Stefan. I didn't even have to bribe him.
What are you paying? Yeah, I don't believe that's saving on it.
The one CPU I know that was designed in cooperation with compiler writers actually wound up with old blend. It has 32 general purpose registers, but some instructions can only access half of them.
Yeah. Save bits in the exactly. Yeah. So that could be a trade-off, of course, that you can only read a certain amount of registers from the 16-bit instructions. That's actually very...
That would be fine, yeah.
What so that was it?
Yeah, that you can only access, for example, the lower 16.
Yeah, Epiphany does that. Bottom 7 registers you get on the 16-bit, yeah.
Well, that would solve.
And ADR does the top 16 registers. I'm also reminded of the 68,000 that splits into address and data registers.
If we look at the strategic requirements, I mean, at the overview it said targeted at large FPGAs. I think it's targeted at small and medium FPGAs. If you're
I think the target has changed a little bit.
Yeah.
Well, I mean,
I don't recall where that comes from.
This is from discussions a year ago.
Yeah.
Okay, so we're refining it. I'm just updating the wiki as we go.
Yeah, I was just wondering if there was a case for it that they have forgotten.
No, Marcus brought it up, I remember, because he said FPGA is getting bigger, and we can fit more processors on an FPGA and do more with them. Not that the processor should be bigger, or that we should not care about the size of the processor.
Okay.
I think it's just that FPGA is getting bigger. That, I recall that was his argument, or that's why we put that in.
Multi-core is one of the things.
But multi-core is still important, therefore, because you want,
Yeah. SMP.
SMP type multi-core. Oh, right, okay, that SMP wasn't a planned, thought it was
SMP multi-core, I mean, what's the main difference there?
SMP.
Well, you can all sorts of...
That you have the same type of cores that are cooperating.
Yeah.
Well, the big little architectures are in to take off. I wonder if we should...
Which?
Big little. Well, that's what ARM calls their mixture of them.
Yeah, I believe Intel has something similar mixed to...
So, like the Tegra 3 that has one low power core.
Oh, I see what you mean, yeah.
So that's not SMP.
No, that's asymmetric. I actually have an ancient asymmetric.
You can have the same size processors and still not be symmetric. You can have... so symmetric tends to be... And symmetric often means shared memory as well.
Forget I said SMP. Yeah. No, track that statement.
No, it's escaped. I'm afraid you can't.
The project is now SMP oriented.
I have an asymmetric multiprocessor IBM PS2.
Oh, yeah.
But it's not actually run in multiprocessor mode. You usually disable the 286 once you do the 386.
Well, that's what I reckon it should be anyway. Targeted at that sort of area. Yeah. So based on that, threw together a bit of a ISA. And I was just going to start banging away on a CGen model, see what happens. But does anyone have any good ideas or suggestions? I was going to talk through the couple of things I thought about for comparing, doing conditional stuff. So do something along the lines of a compare and set flags instruction.
You're on the Google document for the...
Yeah. So the compare and set flags thing, I'm pretty sure how that worked was kind of like how a lot of things work. You have your compare instruction and then you do things conditionally based on that. As well,
you see, you compare and set flags. If you had a an R0 that was writable and fixed to 0, you wouldn't need compare and set flags because you could just do your operations and have the flags set anyway.
Then that's just a subtract with the stored to
Yeah, but it means you save an instruction. You don't need a separate compare and set flags instruction. Of course, if I complained you haven't got enough registers, then tying up 1 to 0 is 0.
Well, it depends on what you can do with your immediates. Because you still need a lot of small constants in such. Or
you need naught and 1.
I think that's right some of the time. But at some stage, you can't, you're not doing an arithmetic option with the thing you want to check, or an arithmetic operation on the thing you want to check.
Well, compare is usually defined to be subtract without changing the destination. I mean, that's all a compare instruction is. So it's not going to be different.
No, but sometimes I assume you meant you have the result of an arithmetic operation,
in the registers.
Yeah, and then the flags are set based on that.
Yeah.
And then you do a conditional thing based on that. I guess sometimes you're not going to have done that arithmetic operation right before the compare, or right before the conditional operation, or I guess the compiler schedules that.
Absolutely.
But in this case, I don't know, maybe it doesn't have to.
I'm just saying that if you don't need to have a separate compare instruction if you have a way of throwing away the result. Because that's all a compare instruction is. It's the subtraction and throwing away the result.
Yep. So we make...
And which bits are setting?
Which bits are what?
Which of these instructions are setting flags? I mean, obviously.
Yeah.
Because you haven't got a column here for...
Compare. That's the one setting flags. Compare and set flags.
Right, so you don't have any set flag instructions as you do today.
That's sort of what it is, right? Set flags.
You've got set flags for bit field and set flags for bit. What do these do?
And test if things are set, or test if fields of registers are equal to something else.
So compare and set flags only set flag. So
pretty sure. Set flags in SPR, comparison with bit field, defined by the immediate, and
I'm not sure you've got the right amount of flag setting going on. I mean, have you said what flags you actually care about?
Yeah, like 0, negative, I don't know.
1's complement overflow, 2's complement overflow?
Maybe.
Well, I mean, do you want?
You can have as many as you want, I think, because I haven't got into those.
But then you need to. But if you're going to do those, you better define how you're going to set them. If you want 2's complement overflow, then are you going to say subtraction set and addition set 2's complement overflow? If not, how are you going to do an addition and know if 2's complement overflow has happened? What about add with carry? Because if you're going to have small instructions, you want to deal with big data, you need add with carry.
Yeah. Well, not small instructions, small data words.
Small
32 is not small. That's small.
There's plenty of examples of programs that have 64-bit things like the time.
Long stuff, don't you?
Yeah.
All good.
All right.
Yeah, all that would be in there. I'm talking about the concept of a compare instruction, but then, I don't know, flag setting based on bits.
I think you've got to be more... I still don't get what this compare instruction does. I mean, compare in every architecture I know means subtract and throw away the result and set the flags accordingly.
Test 2 registers, flags in SPR. Test 2 registers, flags in third.
What do you mean by test 2 registers? What's the operation between those 2 registers you're doing?
I guess subtract, yeah.
Subtract, yeah. So how do you do test for 2's complement overflow on addition?
You got some compare instruction, I guess, and then you define some flags, and it sets those flags comparing those two. But yeah, I agree. How do you test for 2's? Well, 2's complement overflow, that would just happen. You'd set some flag, I don't know.
So the addition is going to set the flags?
Yeah, I guess so.
So why don't you have all your arithmetic operations and not your logical ones setting flags, or define what flags are set by them? I mean, if you have a set of columns for the flags you're going to have.
0 for, it might make sense to set 0 for, say, and that pretty much covers your bit test operation.
Yeah, I mean, yes, there is does this set a flag, does it not set a flag, does it always clear the flag? Because actually, if you say my logical operations do not set arithmetic flags, then I've got greater scheduling options to put an arithmetic operation, a logical operation, and then a test of a flag, or a branch on a flag, in that order. If, however, I say logical operations don't set flags and furthermore clear them as well, then I've got to have my arithmetic option immediately before.
This is a level of detail I haven't gone to yet, but I agree, that sort of thing is needed, but here I was proposing, I don't know, some instructions that I thought would be useful because...
But you have to have that level of detail to know whether you want to compare instruction.
Fair enough.
But you can do some of the big architecture things, like the model we have in OpenRISC 1000 of how you do conditions is you have a series of set flags which give you all your arithmetic comparisons, greater than equal, less than equal, and so forth. And then you have a branch on flag, branch on not flag. That's the MIPS model of doing it. Now, the alternative model is to actually say that flags are set by arithmetic operations directly, and then instead of just having branch, flag, branch, not flag, you have a whole load of branch on pattern of bits. Sorry? I thought the set flag stuff was MIPS. The DLX that comes from.
Okay. So what I was proposing, and it's come back to me now, this compare would do that. So you would basically run through all of those set flag, if not equal to, greater than, less than. You'd have a register with all these flags, then set in it based on that compare thing.
Okay, so it's compare flags. It's looking at
compare two things and then set a bunch.
But why? But you don't need it then. You need branch on flags because what's the purpose of compare? So what's the operation you do after you compare? You either branch or you don't branch. So you want
the reasoning you had when you did that was that if I remember correctly, it's kind of steal some immediate state from the branch.
Yeah.
You have a comparison in there.
Because you lose bits on your branch instruction. But correspondingly, of course, yes, I can do a longer branch, but if I then need an extra instruction, even if it's a 16-bit instruction, it's not paid off.
So if you look here, so this jump is bit clear, jump is bit set. That then basically checks. It's not limited to checking a flag register. So the flags will end up in either an SPR or a normal register. But you can see here that by testing a bit, you know like which bit corresponds to less than signed or something, you know. And then so you jump an immediate. I know that's jumping to a value in a register, but at the end there you've got a 5-bit immediate 16-bit version of this instruction. So
you did some statistics. What's the length of branches? I mean, you've got jumps and branches here. I think in OR1K, branches are relative and jumps are absolute.
Jumps are PC relative in OR1K.
Yeah, I think.
No, if I go to jump.
Both branches.
Jump register is absolute.
But
both branch and jump in OR1K are PC relative.
Oh, the immediate one is relative. Yes, it's relative. Yeah, you're right. Yeah. Sorry. What?
Large jumps.
Oh, you've only got 26 bits. You can't do a jump immediate to more than 26 bits away.
Yeah, so it works right.
It's a limited range.
But then you just load your address into a register and do it that way.
Yeah.
That was the bug.
Ah, okay. PC relative jumping here. Did I even do one?
Well, if you want to have any sort of relocative code, you really want a relative jump.
No, I never thought about it, but anything with an immediate is PC relative. Yeah, here we go. I specify a PC relative jump here.
Yeah. You see, what I would do is make all jumps conditional, and I don't know that's what the question was. What flags are you going to care about? And if you're comparing I think you probably want Z for 0, N for negative, C for 1's complement overflow, typically V for 2's complement overflow. I think those are the 4 common ones that people have.
Yeah.
And put a 4-bit field in every jump instruction, including jump and link, because actually conditionally calling a function is a useful thing. And then you don't need the set flag or whatever it's called here, and you just define your opcodes. And I'm a great believer in the arithmetic opcodes being the only ones that set the carry and overflow, and that logical opcodes don't touch those, so that you've got the option of sequencing. Logical opcodes should set 0 at the very least. Probably not negative, actually. Just 0 is sufficient. That looks good.
I agree with you. But again, yeah, that's the details. We're going to need that.
But then that starts saying, if that's your structure for your instruction set, you then can see this is the group of instructions I need, this is where I need space. And I like other architectures do, the idea that the short instructions have a restricted register range to give you...
I found the branch distance statistics for the Linux kernel and
I mean,
this is the stuff Julius did last year.
yeah, so nothing jumping further than 80 bytes, I assume this is, because everything's divisible by 4.
Yeah. Are you going to allow 16-bit alignment of instructions?
Yeah.
Yeah. So nothing jumps more than 80 bytes. That's 40 half words. So you need. If you restricted that to 64, what percentage would you get?
Well, that would leave out 2.1%.
So you could get 98% of all branches with 32 half words forward or back, which means you just need 5 bits. And you get 98% of the branches.
And there's an immediate with a jump immediate with 3 bits.
It's dynamic 1 bit. It's dynamic linking.
No, because they're relative, so you have to relocate them.
That's pretty good.
Change because
Dynamic
linking means slightly more code for things like a function call, so
it
might jump a little further.
Yeah.
But it doesn't change it by much.
No.
That's not very good with the date.
But it means basically a branch with 5 with 5 bits gets you everywhere you want to for all practical purposes. And if you've got a jump instruction, that gives you quite a lot of scope for the 16-bit instruction.
I've tried to fit in as much as I could into the 16-bit encoding kit.
I'm not sure if 5 bits is actually quite that much, because all of these distances are unsigned, and all the branches are signed, so yeah.
Okay, so you need 6 bits then. So it's plus or minus 32 half words. 6 bits then.
So, I think there's, enough range. I tried to give enough options for doing things conditionally so that for any use case, any case, basically, you can pick a 16-bit instruction to do that.
Yeah. One thing you can do is make your ABI match as well. I mean, if you're going to say, I'm going to only allow R0 to R7 to be used in 16-bit instructions, so I only have a 3-bit register field, then I better make sure that the really useful registers are in those ones, like the link register, the stack pointer, and the first argument register.
Yeah, well, this will be...
I don't think can something with accessing the stack pointer.
This, well, if we do 32 GPRs for the 32-bit instructions, we've got 16 GPRs for the 16-bit instructions.
Why not? Why 16?
So you get... I don't know, because it works.
Well, why not have 8 and give yourself more space in the 16-bit?
Yeah, maybe with...
I mean, the interesting thing is, if you have 8, then that takes 3 bits. Actually, quite neatly, if you then have 32-bit instructions with a matching field in the same place, potentially you can actually have up to 64 registers. You don't have to use them, but it does make your decode logic a bit easier. In that you've always got a 3-bit space, and you just take 2 of them and stick them together for your 32-bit instruction.
Yep, that could be. So I mean, that's
not an original idea, I hasten to add.
the 32 registers thing is going to have to make me rethink the 32-bit instruction. And I will certainly look at the possibility of only using 8 for some instructions.
I think I'm gonna start heading home.
Yeah.
All good.
Yeah. I'll tell you. Okay.
But yeah, I was going to start hacking on CGen, see what I came up with. I've noticed on the CGen mailing list that they may not fully support mixed 16 and 32-bit instruction ISAs. There may be an issue with that.
That's a new one on me. Extensible instruction sets they don't like, but I can't understand why they wouldn't support mixed 32 and 16-bit. I mean, you might be right. I mean, the guy who knows more, I don't know that much about CGen.
It's a little bit old. It's from 2002, this post.
Well, come on.
Hey, it's heater target at arccores.com.
ARC. Oh, right. Okay. So, yes, it would be ARC causing the trouble.
He was saying, yeah, he couldn't get it working.
Well, since the guy who took that over, that architecture, was Jörn.
Oh, yeah.
I did actually set up, he was up until 2 in the morning and he's not answering IRC. But I did try and prod him earlier. I'll put another message.
So that's what I was going to start on at least. Playing around with that. Yeah, it's a big undertaking, but if we got an assembler working first, and then, I don't know, maybe I could look into LLVM to get a C compiler up and running pretty quick. And then we could just do compilation of whatever and look at static code size. Probably get a pretty basic simulator up and running to evaluate execution. You know. The other thing is for the rest of the architecture in terms of peripherals and exception behavior, I was just going to pretty much take what we have in OR1K, but, you know, for cases like exception vectors, you know, their locations and things, make them all parameterizable at runtime and boot time and stuff. So, you're off, man?
Yeah.
Really good to see you again.
Yeah, it's nice to see you. Nice to meet you, Simon.
Nice to see you again, sir.
Yeah, nice to meet you.
We will hopefully do this again sometime.
Yeah.
Yeah, definitely.
Well, we're due to get the 5 past 4 train, so
Okay, cool.
so we'll probably leave in about 15 minutes.
Yeah. Good. Alright, well that's my OR2K, just let me know what I'm doing. And
Yep.
that was very good input. Thank you.
You're welcome.
Bye.
Bye. See you
Hey,
soon.
all, man. Talk to you soon.
Right, so there's us with the bug squashing time.